Hi, I'm Professor Damien Gatinel. I'm an ophthalmologist. I work and live in Paris, France. I'm affiliated to the Rothschild Foundation Hospital and also to the Rabat University of Ophthalmology in Morocco. Well, in the mid-2000s, we were using bifocal lenses which were efficient to restore near vision. But at that time, the patient who wanted to work without spectacles on the computer, which is usually at intermediate distance, they were struggling because there's no foci there. And therefore, I thought that there would be probably a need for a lens which not only provide the patient with spectacle independence for near and distance, but also covers this intermediate zone, which is so important today, especially because since then, we are using computers more and more. Tablets were introduced also around the same time, and I think there was really a place for such a lens. In the mid-2000s, I was using as a surgeon bifocal lenses. I found they were efficient to make the patient spectacle-free for distance and near, that is, reading distance. But the patients were struggling on computers and sometimes also dashboards. And I thought at that time there would be a solution to fix this if you had a lens which would not only cover distance and near, but also this intermediate distance. And therefore, this is how the trifocal idea came. So when we started to design the lens, we had many options on the table. And we knew at that time that diffraction, which is very useful for the purpose of replicating foci, can have also some side effect that you can minimize using tricks like slightly rounding the edge of every step that minimize unwanted diffraction, and it reduces the chance of dysphotopsia. That's why we did that. With FINEVISION, the trifocality is across the full optic, because the trifocality is apodized, and this apodization is intended to take the benefit of the pupil movements. So the pupil dilates in mesopic condition and constricts in photopic condition, and apodization is intended to bring more light for distance vision in mesopic pupil, that is large pupil conditions. So you can cover the full optic, because when the pupil is dilated, there's more light for the distance foci and a bit less for intermediate and near. Whereas in bright light condition, the repartition of energy is different to increase the near and the intermediate foci, because usually when you read, the pupil constricts a bit, or when you are in bright conditions like today, the pupil is small, and there's enough light to split light in 3 foci. The problem is that in mesopic condition, you want to make sure that there's, of course, enough light for reading still a bit in intermediate and near, but that the distance vision maintains sufficient optical quality so the patient does not suffer from any annoyance. Apodization is a way of reducing the height of the steps from the center towards the periphery. And the lower the steps, the less diffraction. So the more distance vision, because the basic power of the lens is for distance vision. What the diffractive element creates is a light split for intermediate and near. If there's no step, there's no light split, right? If the step is low, there's less light split. And when the pupil is large, the percentage of low step is higher than when the pupil is small because of apodization. So this is how you can really differentiate the amount of light you split for distance near and intermediate, and take the benefit of these pupil movements that are naturally occurring. the number of rings on the FINEVISION lens is exactly 26. And maybe surprisingly for you, it's not more than for a bifocal lens. What is different with a bifocal diffractive lens is that the height of each ring has an alternation. Every other step is lower or higher than the preceding or the next one. That's how the lens can induce another foci without inducing the need of extra steps on it. Your question is interesting because I had worked on the monofocal lens that was the base for the FINEVISION, and the compensation was minus 0.11 micron, which was also used for the FINEVISION design. For chromatism, the good news is that for the distance foci, there's no majoration, there's no increase in the chromatic aberration. But for the intermediate and the near foci, there is compensation, which occurs due to diffraction natural properties for the chromatic aberration. So again, the lens does not introduce more chromatic aberration, it just reduces it, but just for the intermediate and the near foci. What is very important in patient satisfaction, I think there are two things: preserving a good distance vision quality and also making the patient able to read without struggling, without having too much illumination. And so therefore, the satisfaction comes usually for good distance and good near. Of course, as I explained, trifocal lenses are justified by the fact that if you have no intermediate foci, you cannot see in intermediate vision. But the energy there should not be very high, because what you see usually in intermediate vision, for example, is a dashboard which is bright, a tablet which is bright, a computer screen which is bright. And I think also when you see those curves, that is in vitro, they look like peaks like this, but in practice, I think you could see it more like a bridge. That is, if you have energy for distance and near and some energy in the middle, there will be a continuous performance that will enable the patient to feel like there's no loss of quality or light intensity between distance and the near. So again, to summarize this, by order of importance, when you operate patients with trifocal lenses, I would say you must have them having a good distance, because they don't want to lose the distance, else you would do monovision, right? Second, you need a good near, because the patient specifically wants to be spectacle-free for reading distance, not only intermediate. And then you don't want them to have this problem of the trough in the middle, but to solve this, you don't need to put too much energy there. And that's why I think this is the best design to have this kind of shape. People usually ask about the central zone. Is this for distance or near? It's for both. The central zone is designed for already getting some light distribution difference between the distance and the near, and the intermediate as well. It's something which in the design comes naturally when you design diffractive optics. So it's for both. Well, to be frank with you, I would say that this change in what should be the best intermediate vision was brought when some competitors launched lenses that were quadrifocal made into trifocal, where the addition power was slightly different. It was a bit more. In fact, you could consider that lens, the Panoptics, as a lens which provides a +2 add and a +3 add instead of something which is going by ×2, like 175, 350 with the FINEVISION. That's why also the diffractive profile is a bit more tormented, because there's no harmonic relationship directly, right? And so by design, this +2 add brings the intermediate foci a bit closer. Does it make a difference clinically? I'm not sure, because again, don't look at those peaks, think more as bridging everything. And when you bridge everything, the middle peak, I think, should be right in the middle in terms of vergence, instead of being too close to the near one. I'm not sure it makes a big clinical difference. I've never had a patient telling me never, oh, I see well here, but not there, or I see good, or I see perfectly here, but here I struggle. Never happened. I think, again, as soon as you have an intermediate foci, and because we didn't want to increase the number of steps on the lens, we found naturally as the most efficient and most elegant method just to alternate the height of the step, but not adding steps. For regular eyes without any refractive surgery or corneal history, I think the formula you can use is the one you're familiar with, but you of course have to choose the formula which performs better for a specific eye given the axial length in particular. I would of course recommend the Pearl DGS, not only because we conceived the formula, but also because it was conceived based on a data set which contained a lot of fine vision lenses. So given this particularity, the formula is particularly adapted to fine vision calculation. It's available online, it's free, it's easy to use, and it's probably at the time of I speak soon to be incorporated in some biometric instruments. For post-LASIK, for post-lenticle PRK patients, you must really use a formula which is adapted to this situation. Don't use SRKT, for example. So there are many on the market. Barrett, Pearl DGS has also an option, complex eyes, where you can not only select refractive surgery history, but also differentiate LASIK, PRK from radial keratotomy, for example. So use a formula which takes this into account. This formula basically, they don't use the corneal information to predict the lens position. And they have also sometimes algorithm which increase the accuracy of the corneal power prediction, which is key in those eyes because the cornea is not a virgin cornea. So classic algorithms do not work as well on those IOL power calculation than the one we have developed since to particularly match those characteristics. It's based on it's adapted to other lenses, but it's particularly the lens we used was this one, by the way. And I would add, particularly regarding the Pearl DGS formula, it was established using a data set which contained exclusively fine vision lenses. So this was the reference lens on which we built the first algorithm. Of course, we then adapted to other lenses, but it's really made from data sets using fine vision lenses data. So the pupil diameter, of course, plays a role. Let's speak about extreme ones. When the pupil is very small in a patient, because the pupil does not dilate, we see this in some patients when they're a bit older, the lens will still work because a small pupil extends the depth of focus naturally. This is a pinhole effect. So if the pupil is small, like around 2 millimeters, you can use the lens. You will still have diffraction because the first step, as we discussed before, is around 1 millimeter, right? And still, the vision will be okay because of this extended depth of focus. In fact, if you look at the theoretical bench performance on small pupil, you will see like almost a plateau through focus MTF, which translates clinically into a full range of vision without spectacles. Now, on the other side, if you have a very large lens, so if it's very, very large, which is very uncommon in the cataract population, also because after cataract surgery, we've measured that the pupil diameter tends to be slightly smaller than before the surgery in mesopic condition. Well, if you have like a 5 millimeter mesopic pupil diameter, it's not a problem either because the pupil will be large in those situations where you have a dim light condition, when you are functioning in mesopic condition, as we say. So when you need more light for distance usually than for near. So because of apodization, the lens will send almost twice as more light towards the distance vision than to the near when the pupil is small. So this differentiation will help the patient to minimize the risk of a halo glare at night And I've never excluded a patient for pupil diameters comprised between around 2 and around 5, because again, the lens is robust to these conditions. The domain of formula optimization is quite interesting, and it's part of the success because you need, of course, to be on target. Optimization is mandatory if you notice that despite, for example, targeting this refraction, the first plus, you have a shift towards minus. How to do it? There are many ways. You can use online calculators on IOLCON website, for example. And we also published lately a method which you can use yourself with your Excel file. There's no need of going online. You can use with any formula the constant change. With SRKT, for example, we can calculate the new A constant that would make your mean error on average 0 and not minus or 2 plus. This is something that you again should be very careful with if you start with the FINEVISION, because you will have to start with the A constant, which is the one the manufacturer will tell you to use, but then you can slightly adjust it when you collect your first postoperative results. And again, there are simplified procedures today to do it. On my website, there's a full page dedicated to this. It's a bit complicated, of course, as this domain is, but at the end, the solution is quite simple to implement in Excel or things like that. Or go online, or do it a bit like empirically, as some doctors do. Sometimes they notice that they can move up or move down the constant like this to improve their results. Why not? So as we said, the FINEVISION lens was the first on the market, and since then, trifocal lenses now are in most of the big players' portfolio, because again, it's so important to provide a full spectacle correction with the IOL. But still, despite the successive introduction of other lenses, I've noticed that my colleagues, they usually go back to FINEVISION after trying competition lenses. I think the reason is when we designed the lens with, at that time, physio R&D department, we had a white page. And for example, as I said, we found it would be very interesting not to increase the number of the steps on the lens, which we did. Second, we used those convolution method to minimize the abruptness of the step altitude height changes. We also used apodization. All these things were possible because we didn't have to try to not infringe on this or not cover that. We were really like exploring the field. And I think, maybe I'm biased, but I don't think I am really, we selected the most efficient, straightforward method to induce trifocality. And when you have the simplest and most efficient probably way to do this, then everything after that is probably at best as good, but probably not as good if you sacrifice this or that on the best recipe. That's my feeling. There were also completely different approaches. We even had pentafold lenses, sinusoidal lenses, but they never took a really significant share on the market. If you think about it, most of the successful trifocal now, and FINEVISION is the most successful in Europe, they are almost based on this principle that you should not increase too much, you should not even increase at all the number of steps, and try to have low steps in terms of height and round steps as the FINEVISION has. So to make it simple, I think we selected the best ingredient for the recipe, and the recipe, to me, is still the best.